All right, everybody, last video and last homework assignment for the week. Don't forget, all of your teachers, including myself, are expecting you guys to do work Monday through Thursday. There will not be nothing new posted on Fridays, just as a heads up. Friday is specifically meant for teacher meetings and for us to get our lesson plans together for the following week. So just as a heads up. All right, pause your video at this point in time, read through the question and try number 1 on a scratch sheet of paper. When you're ready to see the answer, go ahead and unpause. All right, so basically what we're looking at now is instead of looking at square blocks, now we're talking about rectangles. Okay, so we've got something that looks like this, and it says, can you find a different expression to represent the area of this new rectangular block? And can you convince us using a diagram? So before, we would start with an x squared box, right? Or like if we had x plus 2 times x plus 2, we'd add 2 rectangles to both sides. There would be 4 little pieces in the corner. We're good. Well, now we're saying, okay, actually, on one side of the x squared box, we're adding 5 pieces. And on the other side, we're adding 2. It does not matter if you drew 2 on the left side and 5 going upwards. That's totally fine. It's the same exact thing. So what's changing now is instead of having the same amount of rectangles being added to both sides, we can have different amounts. And the same thing occurs. To be able to figure out how many little pieces there are, we need to literally complete the square, or in this case, complete the rectangle. So this expression right here is in factored form. We can also write it as y equals, how many x squared boxes do we have? We have only one. How many rectangles do we have? We've got 1, 2, 3, 4, 5, 6, 7 total rectangles. And how many little pieces do we have? We have 10. So now what we've been focusing on so much is going from standard form to vertex form. Now we're going to start talking about standard form and factored form and how do those two things connect. So there are going to be times like this particular case where Optima doesn't need perfect squares anymore. Now we're looking at possibly rectangles as well. All right, I want you to pause the video at this point in time and try these expressions. Basically what I want you to do is taking the expression, I want you to turn it into factored form by thinking about what this would look like as a diagram. Okay, so let's do the first one together actually, and then you can try the rest of them. So I've got an x squared box, and basically what I'm trying to figure out is, okay, if I have 9 rectangles, how many should I add to each side so that I get 10 little pieces in the corner? So I'm kind of thinking, okay, well, if I did maybe 1 on this side and 8 on this side, well, that's not going to work because 1 times 8 is going to give me 8 in the corner. Then I'm thinking, okay, what if I did like 2 and 7 or things like that? Nothing seems to be working. There is no possible way for me to have 9 total rectangles and get 10 pieces in the corner. So here's what we write. NF, and NF stands for not factorable. Okay, we can't make this picture. It's not going to happen. We can't write it in factored form. Versus if you take a look at 11. Number 11, here's my x squared box. And if I have 7 rectangles to work with, but I need it to be 10 little pieces in the corner, what if I added 2 to this side and 5 to this side? That would give me 10 little pieces in the corner. So if I were to rewrite this in factored form, I would write x plus 5 times x plus 2. Now, when you're multiplying, it doesn't matter what order you're doing, so you can also write it as x plus 2 times x plus 5, totally fine. So at this point in time, if you haven't, pause the video, give this a try, and then we'll go over the answers when you're ready and you want to unpause. All right, so number 12. We've got 9 rectangles to work with, but we want 8 little pieces in the corner. So I'm thinking, what if we add 1x to this side and add 8x to this side? That would be the 9x rectangles we're working with, and 1 times 8 would give me 8 little pieces in the corner. So in factored form, I can write x plus 1 times x plus 8. Okay, if I'm looking at 13, I have 6 rectangles to work with, so maybe I want 8 in the corner. So I could do 2 on this side and 4 on this side, right? Because 2 times 4 is going to give me 8 little pieces in the corner. So I would write this as x plus 2 times x plus 4. 14. I want to use 8 rectangles and somehow get 12. So, 2 and 6. That would work. So there'll be 12 little pieces in the corner. So I'm going to write it as x plus 2 times x plus 6. Okay, hopefully you're starting to look and see a pattern that's kind of occurring. We'll talk about that in a minute. All right, for number 15, I have 7 x's to work with. So what if I put 3 on one side and 4 on the other? That would allow me to get 12. So I'm going to factor this into x plus 3 times x plus 4. Last one, I have 13 rectangles to work with. I'm not going to draw this one out, obviously. But what if I put one rectangle over here and 12, the other 12 over here? That's where I'd get those 12 little pieces. So in standard form, it's x squared plus 13x plus 12. In factored form, I can do x plus 1 times x plus 12. So what relationships or patterns do you notice when finding the sides? Basically what you're looking for is, let's take one of them, like the x squared plus 7x plus 12. Basically what we're looking for is we need two numbers. Okay, so it's going to be x and x. And these two numbers need to add to give me 7, right? So add, like the rectangles are added together. But when I multiply those two numbers, it gives me 12. So if you look at 3 and 4, the reason I came up with that is 3 plus 4 gives me the 7x, the 7 rectangles, and 3 times 4 gives me the 12 in the corner. So that's the pattern. You're looking for two numbers that add to give you the middle number and multiply to give you the last number. So 18, a customer called and asked for a rectangle with an area given by x squared plus 7x plus 9. Okay. The customer service representative said that the shop couldn't make that rectangle. Do you agree or disagree? And can you tell if a rectangle can be constructed from a given area? So if we're using that same idea, we need two numbers that add to give me 7 but multiply to give me 9. Those two numbers don't exist. If I did 1 and 6, those don't multiply to give me 9. 2 and 5, that doesn't give me 9. 3 and 4, that does not give me 9, and so on. So this would be an example of not factorable, or, right, we can't make that rectangle. That's kind of how you know that it's not a factorable quadratic. All right, so here's the deal. The same thing works with, look at, for example, letter B, C, D. You'll start to notice some negatives. It's the same exact idea. You're looking for what two numbers add to give you the middle number and multiply to give you the last number. The part that's going to change is you might have two negatives, you might have one's positive, one's negative, that sort of a thing. So pause the video at this point in time and give these a try. You're converting from standard form into factored form. All right, if you've unpaused the video, you're probably ready to go. So for letter A, two numbers that add to give me 9 but multiply to give me 18. 1 and 8 won't work. 2 and 7, 3 and 6. So x plus 3 and x plus 6. 3 times 6 is 18, but 3 plus 6 is 9. Okay, let's look at letter B. I need stuff that multiplies to give me negative 18. I'm kind of thinking of 3 and negative 6. So here's what I do, you guys. It's totally guess and check. It's not perfect and it takes a lot of practice, but you just try numbers. Like if I did 1 and 18, there's no way that's going to add somehow to give me 3. If I do 2 and 9, there's no way that's going to add somehow to give me 3. So I'm kind of thinking 3 and 6 is the way to go. So I start by putting those numbers and then I start worrying about negatives and positives. If this is a negative 18, I know I want either the 3 or the 6 to be negative, and then the other one will be positive. So then I say, okay, but I want it to add to give me positive 3, so I'm thinking the 6 should be the positive number, the 3 should be negative. That's my process, you guys. It's totally guess and check. There's no perfect way of doing this, and just the more you do it, the better and faster you'll get at it. All right, so looking at letter C. So we're still working with negative 18. So I'm still thinking 3 and 6 because of that negative 3 in the middle. But this time, since I want it to add to give me negative 3, I'm going to make the 6 the negative and the 3 the positive. Look at how similar B and C are. And all that changed was a positive or negative. That's why I'm so tough on you guys about little operations and little steps, is because it makes a big difference. Letter D, still working with 18, but the fact that I want it to add to give me 9 makes me think that this might be a little bit different, but Actually, now that I think about it, what if I do -3 and -6, make them both negative? Then they'll multiply to give me positive 18, but add to give me -9. That's the way to go. All right, letter E. Oh, okay, so things that multiply to give me 4. Well, my only options are 1 and 4 and 2 and 2. And 1 and 4 I think is going to be my only option to try to add to give me 5 somehow. And I want the 5 when you add them to be negative. So if they're both negative, let's try it. -1 plus -4 is -5, but -1 times -4 is +4. So we're all good. Yay. All right, letter F. I think I'm still leaning towards using 1 and 4 rather than 2 and 2 because of the 3 in the middle. And since the 3 is negative, when I'm adding, I want the 4 to be negative and the 1 to be the positive. Last one, I need two numbers that multiply to give me -15. So here's another route. If you're struggling with this, I start thinking about these factors first. So I can do 1 and 15. I could do 3 and 5. And that's about it. Looking at those two options, you can kind of tell that 3 and 5 is going to be the way to go to somehow add to give me 2, right? So if you're struggling, that might be something that can help you out as well. So you start with, okay, don't even worry about positive, negatives, anything like that. Just go, okay, I want to use 3 and 5. So I want to add and get a 2. So let's make the 5 positive and the 3 negative. When I multiply them, I get -15. I'm good to go. All right, so here's the last thing I want to show you guys really quick. How can we factor the following? We don't know how to factor when a is anything other than 1. So if you look at all three of these equations, we don't know how to do that. We only know how to factor if it's a 1x squared. Well, here's a little trick. You see how all of these guys divide by 2? What if I take a 2 out of the entire expression, meaning I'm kind of like anti-distributing, kind of like we did with completing the square. And then I factor what's left over. Two numbers that add to give me 8 but multiply to give me 12, 2 and 6, and make them both positive. So you can factor. This right here, taking out the 2, is called a GCF, a greatest common factor. So for example, if I look at the second one, notice how you can take 3 out of everything. So 3 is our greatest common factor. So I'm going to keep the 3 there and factor what's left. Add to give me 7, but multiply to give me 12. Let's use 3 and 4. Notice how the GCF still stays out front, okay? Don't get rid of it. Last one, what if there's a negative in the front? The easiest way to do that, you guys, is to take the negative out and then factor what's left. So we've got, let's use 12 and 1, and we'll make them both negative. And so that would be my factored form, okay? All right, you guys, this is your second homework assignment for the week. Remember to submit a picture of your homework under the tab that says Chapter 9 Homework Number 2 so that I can give you credit for your remote learning for today. Nice job. You have the rest of the weekend off, so yay, and I will see you again on Monday.